develop very mature theory. Any question? So it would be great if we can have our system linear, right? So if not, can we make it linear? This is the subject of today. I'll erase this. Any question about this? Feel free to come up with any question, please.
So,
Yeah.
I think we haven't tried anything for linear systems other than linear state feedback, right?
Why we were going to introduce nonlinearity, right, in your systems if it's already linear?
I don't know.
To
maybe-
achieve what? I mean, what you cannot achieve here, that for which you need to introduce an additional controller.
Robustness, maybe?
Well, you can achieve it with linear controller, right? So this is a very important point. Is that I skipped this. I just try to dump everything upon you guys, but you know, there is an interesting theory and story behind each line D. So for example, the pole placement, right? Although I don't like it in particular, but we have to give it the credit. So the pole placement, for example, we know that our transient response, settling time, overshoot, things that are very tangible. So if I give a command to my airplane to achieve a different altitude, theta 5 degrees, for example, during this excursion, the airplane will have some transient, right? Okay, this transient will settle after some time, settling time, and it might have some overshoot in the middle of the excursion. So the settling time and overshoot are dictated by the location of the poles. So if I can place the poles wherever I want, this is great privilege. And this allows you to do, you know, very exotic things, like, okay, here is a Boeing 747, it's huge airplane, I'm gonna demand it to settle in 0.01 second with 0 overshoot. Well, that's perfectly fine. The pole placement technique allows you to do that. At least theoretically, practically you will not be able to do it because your control will be saturated, right? Your elevator will reach 30 degrees and cannot move further. So you will not achieve it, but theoretically you can do it because before this controller, before this formulation due to Kalman, indeed Kalman was the first one to represent the control system on this form. Before Kalman, before the 60s, we used to formulate the control system in a transfer function, frequency response, and these kind of things. So Kalman was the first to say, hey, we're gonna, you know, make a paradigm shift. We're gonna represent it in this form, and the whole theory fall out. Okay, before the pole placement and state space modeling, could you even achieve it theoretically? Can you make a Boeing 747 settle in 0.01 second with 0 overshoot? With the techniques that we had in classical controls. PID, lead, lag, and so on and so. The answer, of course, not. Because I can try to, well, PID, which is the paradise, is like 95% in the industry, but the three gains, at most they can move 3 poles. And the rest, the airplane has 9 poles, the rest you have no control over whatsoever. So they will go on whatever places. You hope that they go in good enough places, but not arbitrarily desired places, right? So at least theoretically, you can achieve whatever you want here, pole placement. The only issue here is you need full state feedback, and that it doesn't control the steady state error. But these things have solutions. You can add an integrator, you can do all sorts of things. Anyway, so this is a review. This is 270A course. This is just a review, nutshell, to motivate, set the stage that we really want systems on this form. It would be paradise, right? If we have a system on that form, x dot equals ax plus bu. Any questions so far? Please, if you have a question, just let's discuss it.
Doctor, how can I come up with the matrices Q and R?
Yeah, this is a very good question. These are typically set by the user, which means that it's based solely on experience.
Okay.
Okay. Yeah. So practically, it's try and error.
Mm-hmm.
There are some standard techniques, but no fundamentals behind whatsoever. Okay. So we want to do linearization, And don't get me wrong, linearization is to make your system linear, right? We have a nonlinear system and I want to make it linear. Well, there are two ways of doing that. There is the baby way that we learned in our undergrad by doing approximation. So whenever somebody mentioned linearization, this is the thing that jumps to our head, right? Is that, okay, we're gonna just approximate our system by a linear system, and this is okay, it's valid for small neighborhood, right? But there is another technique that is global. Is to render your system exactly, not by approximation, a linear form. So this is, I will transform, this is transformation. I'm looking for a transformation that gets my system into a linear form exactly. And maybe a combination between transformation and feedback. So I can choose my U freely, so I will play with U. So this is and or, actually, feedback. So what do you mean by transformation and feedback? So let's see. So transformation first. This is the topic of today. Okay. Of course, I will not talk about approximation. You guys know it from your undergrad. Transformation and or feedback. What do you mean by transformation? So actually, this question was posed and answered by Poincaré and independently by Lyapunov in the late 1800s. So they posed the following question. I have this differential equation. It's non-linear. There is no control. It's just a differential equation. Well, I have to remind you that there is a theorem that says, given any f vector field that doesn't vanish at a point, there is a coordinate transformation that makes this guy looks like a constant, like 1 zeros, right? There's this theorem. So practically speaking, all vector fields, if they don't vanish, they look the same because you can transform them to be constants. But the thing become interesting if they vanish. If they vanish like at some point. So this is an equilibrium point. Okay, they were interested in the following question: does there exist a transformation T of x such that for the new variable the dynamics is linear? Very cool, right? You're going to analyze your system in the transformed variable, in the transformed state here. Check the stability by eigenvalues of A, we have the paradise, right? If and only if condition, everything is easy and nice. And actually the answer was yes, they give a sufficient condition. Very interesting in terms of what do you think the sufficient condition will be based on? So you're given this guy, and I'm asking, can I transform it into a linear system? So all the information that I'm given is just f. And I know that it vanishes at a point, and I want to do this in a neighborhood of that point, so it's in the terms of eigenvalues of the Jacobian. Right? The eigenvalues should lie on one side of a line in the complex plane through the origin. So something like that. Okay? One side of a line or the other way. But if they go everywhere, then, well, their theorem is not conclusive. So that's interesting, okay, but this is transformation. We have more freedom here because this differential equation didn't have free parameters, didn't have control. Our differential equation has control, has free parameters that I can play with. So I can relax this condition a little bit and play with my control. Actually, I can rely solely on my feedback if things are nice. So here is a naive example for the feedback. And indeed, it's a naive example. I have x dot equals f of x plus g of x, and these are scalars. This is why it's a naive example. These are scalars. And obviously, g of x has to be not 0, right? Because if g is 0, then you don't have control. Okay. Well, I can define let your control, well, it's free parameter, right? So I can define it the way I like. And in particular, because g is invertible, I can divide by. So, and if you divide by, you cancel the g. Then you have freedom to choose whatever next. I can cancel the nonlinearity, so I have negative f here, and then I can add whatever I like. If you like ax plus b, new control v, okay, here it is. So in the new control v, the dynamics is x dot equals ax plus bv, right? It's just I cancelled my nonlinearity. And here I was able to do it because I have full control authority. It's one state, one input, right? So whenever you have m is equal to n, you can do inversion. You can do inversion, but this is too luxurious. So it's hard to rely solely on feedback, and it would be wise if we can combine both, okay? You have some time to write while I'm raising, and please feel free to ask questions. Anybody didn't get the objective of today's